All right, welcome everybody. It's good to see everybody here today. Couple announcements up front. As you probably have heard, today is our 1-year anniversary as a user group. So, yeah, very exciting. This is a pretty large group. We've really had great turnout. We've had great speakers. Already have the next 5 speakers lined up, so there's a lot of interest in the community. And I just want to say, if you've been a speaker here, I want to say thank you very much. Really appreciate it. Another round of applause for all of our speakers. Also want to thank Jessica in the back. She has been a tremendous help. We originally were talking about working with Techlahoma. I had no idea what that meant. It just sounded good. And Jessica immediately helped me out with all of the admin side of things, getting the food and the hookup with Techlahoma and the event space. So that's been tremendous. So hats off to Jessica. Thank you very much for that. And then also anybody here that is part of Starspace, I also want to thank Starspace for letting us use the place for this long. So that's been also very nice. So there's cake in the back. Don't be shy about grabbing some. Okay, a couple announcements. We have it's the, I'm sorry, I'm going to forget the name. Free Code Camp OKC is coming up next month. And if your business is interested in recruiting as part of that, please see Kimberly in the back as soon as you can, because the deadline's quickly coming on that. So if that's something that your company might be interested in being a part of and getting connected with that community, please talk to her. All right, I'm going to hand it off to Mark here. Mark Smith comes to us today to talk about Apache Spark and some of the interesting workflows that they use. He's with Sonic and has been doing a lot of their big data platform. You probably know Mark. He helped found, I think it was the Java user group and the big data user group. Is that right? And the Techlahoma user group. Okay, so he's out there. So you guys probably already know Mark. I'm going to get out of the way and hand it over, but thank you.
Thanks. So, yeah, go ahead and clap, Phil. So my name is Mark Smith, and I've been running the Big Data User Group for 3 years now. We had our 3-year anniversary last month, so we're pretty excited about that. Actually, we had 2 people from Augsburg at our very first meeting. Yeah. So I have been using Spark for a couple years now. Love it. Really, really think it's powerful. And I look forward to explaining it to you. I'm more than open to questions even up front. Do you guys have any questions or thoughts around Spark or what we're going to talk about? No? Is anyone wondering why are we dealing with Spark in a functional programming meetup? Is anyone actually wondering that? Or is anyone like, yeah, I know exactly why? No? So, I'm sorry? Somewhere in between, right? Spark is written on Scala, right? Because it was the perfect way to do this resilient distributed data set system, right? This immutability nature of functional programming, along with the way it allows you to distribute and thread data is very powerful. And you probably wouldn't have something as effective or as valuable as Spark without the functional programming concepts built into the programming for Spark. One of the reasons you find Scala and Python as a first-class language within Spark is because of its functional programming nature. While it supports Java and R, if you've ever try to do Spark in Java, it's quite painful, right? Even with Java 8, it's still very painful. Of course, Java 8 is pretty painful, so. All right, so any questions at all? Any thoughts? No? You guys ready to go? All right, so I did this initial presentation. We're going to be exploring the basics of Spark, basically RDDs and DataFrames. Since I wrote this presentation, they've added datasets and structured streaming. And when I started looking at adding that to this presentation, there was like, no way. But I think it's best to get down to the foundation, right? Then you can build on top of that foundation. So that's the goal. But it's at a functional programming class, so I have to put a functional programming slide in here. And hopefully this will start a lot of arguments, right? Because no one can agree on what actual functional programming is. But But when you look at actually Spark, you'll find that we have two REPL kinds of approaches. There's the Spark shell, which is Scala, and then there's the Python shell, which is for Python, right? Then we have basic mutation, right? Once you create an RDD, that's it, right? You can't modify it. You can, of course, create a brand new one, right? That's immutable as you wish. I love not getting nulls because have you ever, like when you're doing like a map on your little computer, right? And you get the null, it's kind of easy to trace it down. But if I've got 50 computers, and on those 50 computers, I've got 30 processes per computer, and in those processes, I've got multiple threads running, where's the null? All right? It's almost impossible to find, right? And of course, we compose by functions. That's really the thing that makes Spark amazing, is the functional nature of how you build your programs. So I think it's really cool. And also you'll find that Spark is really lazy, right? It does not do anything until it absolutely has to. And it only does the minimum amount to deliver what you requested. So that's really nice in your REPL approach, right? That repeat and try and repeat and try. It's been really, really nice. And we love the sort of other interfaces we get, like IPython or Zeppelin. Has anyone used any of these things? Actually, it's not IPython, it's iNotebook, or what is it? Do you remember, Bobby? What's the thing that, Jupyter, huh? Jupyter, yeah, that's it. All right. So what is Spark? And there's more to this now, but Spark is basically this fundamental approach. The bottom thing is the core of Spark, which is resilient distributed data sets. They're RDDs. On top of that, they do a lot of other things. Graph database manipulation, machine learning algorithms, Spark streaming, Spark SQL, and now structured streaming is on top of that. So at its core, Spark provides a distributed system for managing memory and CPU, right? It sits on top of Yarn or Mesos and goes out and says, hey, Yarn, I'm going to run this job. I need this much memory. I need these many CPUs. Give it to me. And then I'm going to put all this work across it, right? So you have a list, right? And you say map. It all executes within your CPU, right? Within the system you're running, within the Spark process, right? Now, if you say to an RDD within Spark, hey, run a map, I'm now running a function on every CPU out there that Spark is using, putting it in the memory on every system that Spark is using. So with map, when you're using your map function, you're limited by the machine you've got, right? When I run map, I'm limited by my 50-node cluster or my 100-node cluster. So I can process a couple of trillion sets of data within some type of reasonable amount of time, right? Right? So you want that big O notation of work, right? That big O notation that says, hey, it kind of speeds up here, but then it kind of levels off, right? This logarithmic curve, right? Here's 100,000, here's a million, here's 10 million rows, right? Over here's a trillion, and it gets crazy, right? Well, that's what Spark gives me. But it gives me it in the way I know how to communicate with Scala or Python. It's not some new thing, right? It's literally map, and it's literally a function. Now, the function has to be serializable because it has to go across a huge cluster. So we've been talking about resilient data sets, right? They're immutable, fault tolerant, all that's managed by Spark, but they're fundamentally a collection of objects of data that I can execute functions against. They're immutable by nature, right? We talked about that as a key part of the functional programming language. It's also, with RDDs, they're completely whatever you want them to be, right? Whatever you want them to be, that's what they are. So they can be an object, they can be multiple functions, they can be, but finally it's just a set of data. And then you have all sorts of transformations, right? map, flat map, filter, join, reduce, all the basic stuff you can run on a list in Scala. But you're not limited by how much memory and CPU you have on that one machine or within that one process. Now, if RDDs, right, are sort of the assembler of Spark, right? DataFrames is sort of the, let's say Java, maybe C++, it's not quite Java. And DataFrames begins to give us a far more sophisticated interface. Now, I get this discussion, and it's always interesting. Hey, if I did it in RDD, I can make it go faster. And that's probably true, right? If I did it in assembler, I could probably make it run faster. It'd probably take me 3 months, right? But I could also use a compiler that knows how to make things go fast and just let the compiler figure it out for me, right? This is what DataFrames is, right? I want to do something sophisticated across a large set of data set. Now, do I want to write it all in RDDs and functions in Scala, or do I want to use the SQL engine built inside of Spark to execute and modify my large data set? So that's what DataFrames is. Now, what they've done now is they've come across and created datasets. And datasets has all the functionality of a data frame, but it's limited by the value object or the object you're manipulating. What that gives you is compile time verification, right? With a data frame, I don't know if I've got bad compile time data, right? I don't know if I'm using a column that's not there. But with a data set, I know exactly what columns are there because I've defined it in the language, right? So data sets give me compile time verification of the data I'm working with. Does that make sense? Yeah, okay. So data frames, data sets, they're associated. How does it work? All right, so A is an RDD. And A is broken into 3 partitions, and those partitions can be executed on in parallel, right? So if I say, hey, run this map and multiply all my integers by 2, right? I'll get 3 of those executions occurring at the same time on my RDD, right? So it's a way of spreading and distributing data across the cluster, right? So what I'm doing there is in stage 1, I'm doing a group by. And a group by does a shuffle. And what that means is I don't have all my work in a data set, right? One small partition, which results in another partition. What it means is I've got this partition, and it's going to affect all these partitions, right? So a group by or anything in shuffle is a performance issue. You got to think about that when you're doing Spark, right? All right, if I'm going to have to move data between partitions to get this, let's make sure that that's worth the impact. But C to D doesn't do shuffling. It's a direct partition to partition development. Then I union D and E to get F, which is now a larger data set, twice the size. And then I do a join. Is a join a shuffle? No and yes, right? So B to G is not a shuffle. But when you start unioning or joining F, then F shuffles. So you have to think about that. That make sense? So that's kind of what's happening there. That's the way it manages large data sets. So if I got 1 million rows, and I've got 100,000 rows per partition, I've got 10 partitions, that means I go to Yarn and say, hey, I've got this much data across 10 partitions, give me 2 CPUs plus this much memory. Yarn gives me 10 instances, and then I go and I say, execute this one thing, and Spark says, okay, execute it across my 10 partitions, right? If it needs to be 50, it needs to be 100. As long as I have the cluster, it works, right? If you don't have the cluster, Spark is smart enough to go, all right, we'll run these 50, and then we'll run this 50, and we'll run this 50, and we'll be done. But when you start doing that, shuffle gets even more ugly. All right. So the other day, I want to go over and point at the screen, but I'm not because of the camera. That's why I'm shuffling around. So I had a problem. We were reading data out of Kafka, and we're reading it through Storm, and then we were putting it on some disk. And we noticed that we're getting duplicates. So we needed to do 2 things. One is we need to figure out what's duplicating so we can go back and find out what's going on. And two, I needed to remove those duplicates. All right? So I'm going to explore this problem set. We're going to look at what happens in an RDD. So I've got this college, right? And it is a string. I read it in, I got a string. So it's an RDD of strings, right? And then I say, hey, across this string, remove my duplicates, right? So then it generates, right, two partitions that have those duplicates. It's pretty straightforward, right? I used the word distinct. Has anyone used that before? Anyone use Scala, right? Well known. It executes across the cluster. Things are good. But that's not good enough for me, right? Because I want to find out what was duplicated, right? So I generate a key, all right? So I want a key indicating uniqueness, all right? So I generate this key, this tuple. Well, first I break it into an array, so I know it's a CSV, so I split it. And then I turn around and I create a key, and now I have a keyed, right, set of arrays that I can then look for duplication. All right? So now that I've grouped it by key. If you have a key, put it in the array. Now I have this first key that has 3 items in the array, so that's a duplicate. Second one has 2. The third one only has 1. That's not a duplicate. All right, pretty straightforward. Then I can use a filter, and I can get a list of all my distinct, and then I can get a list of all the ones that I've duplicated. So now I've got a distinct, unique set of data, and then I've got the list of duplicates that I can begin looking at those problems. So I'm sure all these faces are like, this is complicated. Well, the beauty of learning is duplication. So I'm going to do this again. Well, I'm going to do it in real time in Spark. I may actually sit down for this. Actually, move this down here a little bit. All right, so Spark has a shell. Spark has a shell, and I've actually already created college. All right, and basically what I've done is I've read in this text file. Pretty straightforward. I can do college and do a .take and do the first 2. All right. College is basically an RDD of strings, and it's only, and because it's such a large file, right? I'm only seeing the first line, and the first line is a header. Pretty straightforward, right? So let's do a college count. All right, so 785 lines. Now, there's actually no duplicates in here. What I want to do is actually, I created another file that actually has the duplicates in it. But what I wanted to show you before I do that is if you look at college, there's all the methods I can run on it, right? Coalesce, reduce, map, flat map, group by. It's all pretty straightforward. Now let me show you this. I create a list called my list, right? And I take my list, oops, and there's all the methods I can run. Map, reduce, filter, flat map, float left, fold right, take, head, zip, they're all there. What you actually see is an RDD pretty much looks like a list or a map, right? It's functionally very similar to the concept you're already using if you're using Scala, right? But what it does is, it does it on a very large cluster and works across millions of rows. All right, and because you don't want to sit and watch me work through my syntax errors, so this is, so I'm going to read in a text file, right? And let's see how many there are. 9,000, right? So let's do a college, do dot distinct. Let me set it to some value. Now, I can't modify college, right, because it's immutable, right? But I can modify it and create a new one, a new RDD, right? And I have a new RDD, it's an RDD string, exactly the same time, and let's see how big it is. Again, this is why I have a 7805. So as you can see, I added about, what was it, 1195 rows to this as duplicates. But what does this not give me? Right, so I don't have any idea what was duplicated. All right, so what do I need to do? Do you remember in the original one? Do it. Do a map reduce, right? That's where you want to go. But I need to create a key, right? Now, I happen to know something about this data set, and I know the first 4 fields, right, will identify uniqueness. So what I'm going to do is I'm going to create a key and associate it with that array. But first I have to turn it into an array. So here I am. I'm going to turn it into an array by simply splitting every line, right? Do you notice how fast that came back? Does anyone know why I was able to split that so fast? Because what? Because it's Scala and because it didn't do anything. It's lazy, right? I have not asked for any results of that split yet. So it's not doing anything, right? Now let's go ahead and create a key. All right, so here's my key. And that's going to create a tuple, right? Again, super fast. Didn't really do anything, did it? Now, well, let's ask for those result sets. Let's go to CK rows. Oops, C. And let's just do a count. All right. So that should have took longer, but anyway, CK rows gives me 7805, which is what we expected, right? But what have I got? I got a string with an array of strings, right? So what that means is all my duplicates, my array has more than one value, right? So if I did an array link, anything that's above 2 or 1 means that row was duplicated, right? Because that key indicates uniqueness. All right. So what do I want to do? I want to create a group of distinct values that I can use for my analysis, and then I want to create a group of duplications so I can find out what my errors are. So anything with length greater than 1 is going to be duplicated, right? I think I actually need CK rows, don't I? All right. So how long would cdupes be? That's not right. What did I get wrong? Okay. I forgot to do the group by. Okay, so cdupes count. Notice it's taking a while. What happened was it waited, right? And then it gave me my duplicates, which of course is 0. This really worked last night, I swear to God. I'm sorry? Yeah. So let's go ahead and just overwrite that, right? That's that. Then we'll group it. Still 0.
Because you're using college instead of college students incorrectly.
It might be. Where am I doing that?
So here, zeros. The zeros is back from college. Yeah, yes, that's right.
Right. Okay.
So that's, yeah. That's zeros is college.
Right. So it should be college dupes. All right. Is this right? All right. All right. All right. So now I have 1195 in duplicates, and then of course I can take the first item off the duplicates. See no dupes, and see no dupes. Dupes.count is 7805, right? It's pretty straightforward. That's how it works, right? RGD. There's a lot of code, right, to get that? Did it seem like a lot of code? No, it didn't. There's always shaking their head. It's actually when you think about how difficult this would be in something else, it's probably like not code at all. Does everyone kind of see the functional programming nature of it? Yeah. All right. That being said, let's take a look at DataFrames. So, want to look at DataFrames? Okay. As you can see, it's actually a lot less, right? So we'll read it in. And I'm doing a CSV, right? So if I do a df show, so there it is, right? 20 rows. That seems like a lot. Maybe I don't really want that. Let's do this. I want one row, right? And I want false. False actually says stop making things smaller, right? So this column here, right, went all the way out, if that makes sense. So it's pretty straightforward, right? DataFrames has what? DataFrames has structure, right? A well-defined structure. When I said read a CSV and the header option is true, right? It used the header to define the column names, and then it inferred the type of data I have. So let's, I mean, I don't have it memorized, but it basically goes through the data set and looks to see if there's anything that looks like a string, right? So, oh, there's a string in here, even though there's some integers in here. Oh, it looks like these are all integers or these are doubles, right? So that's what you got, right? So there's my schema. String, string, string. I'm seeing a lot of integers here. No, it really inferred strings.
So does it just default everything to string?
I think it did. I think I had to, maybe I should have put the option into infer. But when I looked at the, so when I wrote this, it was for 1.6, and you had to say option, infer schema true. And then I moved this to 2.1 last night, and it said you don't have to infer schema, it will do it for you. But it doesn't appear to be inferring schema. So I guess you do have to add it. That's probably one of those things you want to check, but that's a good question, right? Or maybe it's not a good question. Everyone's looking at me like I'm crazy. All right. So once again, right, distinct. Right. The count. You notice that distinct didn't really do anything. Again, it was lazy because it didn't really ask me for anything, but my count makes me do something, right? So 7805, that seemed to work. Now, what did it do? It actually looked at every single column, Now that can be expensive. So let's say I want to get a little smarter about that. I know the first 4 columns are actually an indicator of uniqueness. Okay, apparently there's not enough room here. So let's take a look at that. DFDD. Now is this going to take some time? Again, we got our laziness, right? 7805. So those 4 columns do indicate, and it was a little faster that time because it's only looking at 4 columns. A little nicer. So what does DataFrames start to give me? It understands the structure, and therefore it allows me to execute more interesting types of things against it, right? Now I want to get which ones are duplicates, right? So I can group by and then simply do an aggregation and create a value called count, right? And then I can do a df count, right? Dot show 20, comma false. All right, there it is. So everything that has 2 or more on it is what? It's a duplicate. Right? So I can do some quick SQL here and find out. I can do a filter, right? On one count, that would be all my duplicates. I can count them up, right? They should be 1195. But DataFrames begins to give me a far more sophisticated workhorse, right? And because the SQL engine is very sophisticated, you often find much better performance through DataFrames than RDDs itself. But it's all built on RDDs, right? Which then ultimately gives that interface. Right now I'm writing a sort of an architecture document comparing, because we're creating a data pipeline system at Sonic, and I'm comparing Spring Cloud Dataflow, Apache NiFi, AWS Glue, and Spark's structured streaming, right? And here's the deal. NiFi, Spring, they all have a very cool way of getting work to go across, right, in between nodes. They have a really cool way of expanding, right, across a cluster so that it can scale, but none of them have an RDD. None of them can take a very large data set, right, and treat it as a single item and give me a very sophisticated interface into it to manipulate it and transform it. So if I've got a data set coming in, say, to Spring Boot, all right, not Spring Boot, but Spring Cloud Foundry, what I get is a series of microservices, right? So that means I'm responsible for dividing the data up, putting it into the multiple microservices, when it's processed, getting into the back of the end and putting it back together. But in Spark, it does it all for me. Right? I don't have to write the core of Spark to use Spring Cloud Foundry, right? I don't have to do that, Apache NiFi. If you're using Storm, you're going to have to write that, right? Apache Storm. So that's what Spark begins to give you. This RDD concept, the data frames, the data sets, that's its fundamental value. Large data sets managed to scale. Right? Does that make sense? All right. How are we doing on time? 12:13. I guess I had time for data sets after all. It went real slower last night, I guess. I guess I'm more interesting to myself. So, questions? Thoughts? Okay.
So when you were using val for assignment, and it was still lazy often. Is there still a concept of lazy val, like the actual keyword lazy val in Spark, which is kind of slightly different than
Right.
the Scala?
Right. So, an RDD, I'm sorry, what? Oh, sorry. Glasses, apparently. So he asked if there's a concept of lazy val within Spark. And no, not the Scala concept. But basically what happens is an RDD is a set of transformations. Huh? That's true, yeah. And it would work.
Like anything like a Spark looks very similar to like two screens or something like that, but even though it doesn't mean it's turned to a val, it's lazily populated.
So when you did the count, if you had assigned the result of that to a lazy val, would it have?
It would have calculated whatever it's called.
But an RDD is not necessarily a set of data, it's a set of transformations. Right? And then it executes the transformations as needed. So when I said, if I had said take 5, it would have done the transformations necessary to give me the first 5. It would have not done the transformations to do the rest of the 10,000 rows. So RDD is a little smarter about it. Does that make sense? So if I do a show 20, it does enough transformations to give me 20 rows. Right? And that's really nice when you're doing this, right? You're trying to figure it out, you're putting your code together, you're testing it. There's some real value in that. So I'll give you an example too. We were running a machine library called FB Growth, and that identifies item sets that are used more frequent than others, purchased together more frequent than others. Surprisingly, it's Coke and hamburgers. I guess it's not that surprising. So we ran it, and it took 40 seconds to do all of a year's worth of ticket data to tell us what the most frequent. Now we wanted to do that by DMA. DMA is a market analysis area, right? So Oklahoma is a Nielsen DMA, right? And that's how you spend money on advertising across DMA. So we wanted to do that by DMA. That means we have 300 DMAs, so we ran that 300 times, and it took 20 minutes. Well, actually, it took 7 hours. Right? So there was some filtering, right? Some RDD kind of stuff that was done beforehand. We were doing it 300 times. What I did is I did it once, and I used this concept called a cache. And what happens is the results of that value are now put inside a memory, and they don't have to be executed over and over again. That's one of the things with an RDD is because it's lazy, but if you run it 10 times, it'll run 10 times, right? So I put it in a cache, I stored the results of that, and then we broke it down by DMA, and it took about 4 minutes to run, right? 6 hours, 4 minutes. So cache can be really powerful, but you have to be aware that RDDs are doing that. They're just transformations. Does that make sense? Yeah. The frequency analysis was a machine learning library within Spark. We just called it, right? We gave it the data. It gave us a frequency number, a ranking, and that kind of thing. So it was really cool, yeah. So that's one of the powers of Spark, right? Is we're creating this, we're trying to determine what customers are likely to come back and how likely are they to come back, right? Well, we've had a hard time finding that within machine learning, within the Spark machine learning. So we had to go out and get some Python code that does it for us. So we've got some Python sitting next to our Scala code. But guess what? It doesn't scale. It won't scale into a large set of data because it's not using RDDs, right? So we have to really aggregate it up and limit it and then hand it to that thing. Yeah, you have to do the data science part of science, right? All right, how's my R mean squared? How does it look? That kind of thing. Yeah. Other questions?
You did it in CSV. Does it support any other kind of data structures?
Oh, okay, good question.
Your screen came on that part.
Yeah, I know. Apparently my mouse isn't working either. Here it is. All right, data frames are good, data frames are good, data frames are good, data frames are good, data frames are good. Oh, okay, so there's a couple of really interesting formats out there. And if you're doing big data, you're probably aware of them. There's a CSV, There's JSON. JSON is wonderful because it's self-replicating. The problem is it's self-replicating a billion times if you have a billion rows. What we recommend is you've got Avro, which defines a schema one time and then applies it to all the data, right? Now, the thing we really like is Parquet, because Parquet gives me an Avro schema, right? So here's the schema. I define it once. I don't have to find the schema every row, right? So it reserves data. It then stores the data, right, in a compressed format. Right now we're using Snappy, right? And it gives me a columnar interface. Does anyone know what a columnar interface is? So you notice that my rows had 50 or 60 columns, right? But if I only need those 4 columns to do what I need, Parquet will allow me to query the 4 columns and get only those 4 columns. And if you have 100 million rows and you don't want to read 30 columns, I don't have to, right? So you begin to find a real performance improvement, right? It's compressed, so I'm reading less data off the disk. And I'm also reducing, I can also go in there and pull only out of the file that I'm interested in. So we're really moving to Parquet. Right, Parquet is a really powerful storage format. There's another one called Orc, and Orc is slightly faster if you're using Hive. It's a columnar storage format with a defined schema, but it uses the Hive catalog, and it is Hive-based. You can access it through Spark, but you have to access it through the Hive context, not the Spark context. So, other than that, does anyone else know of other data formats or data storage formats that are, anyone else use different storage formats? That's correct. Yeah, yeah. Yeah, it really depends on how you interface, right? You can push a lot of the work down to the database and get a subset out. It's pretty nice. What we do with Redshift is the Redshift interface, right, that you can get actually does a database dump of the data you want, puts it into Parquet format on S3, and then you actually read that itself. So you can do a couple of things there, but it really depends on your database and how effective it is for Spark to read. Mongo. Yeah. Yeah. Any other questions?
So you said that, you got to start with the cluster and then get the code serialized, there. Is that through a jar file or how is that done? Do you have to share a jar file?
I'm sorry, could you ask your question again?
Yeah, so you said you've got a cluster and you're trying to run all these functions on different machines.
Okay.
You have to load that jar file that has those functions in, or does it
Yeah.
send that code over required to?
Yeah. So when you're loading a job, right, you've developed the job, you've unit tested it, it's ready to go, and you want it to run in the cluster. There's a Spark load function. You give it a jar, you make sure everything's included in it, and then Spark will put it on all the machines, right? And then when it's executing, that will happen. One of the things they keep promising us is that we can simply update the jar as it's running, but that still hasn't happened. So if you need to modify the jar, you have to shut the whole thing down. You have to shut the cluster down. You have to shut your yarn cluster down. Start the whole thing over again.
Is there any concern about security with that? I mean, does it lock things down so you can just run whatever code you want? Or some hacker wants to run your Spark cluster?
Have you heard the impression that both the Python and the Java were API interfaces that were data frames? For example, like Python, you can load lambda, it doesn't have all of the functionality of the scale interface has. So, is that, am I wrong?
No, you're 100% right. So the Python code that we're running to do the customer attrition issue, we had to write some special code that starts to cluster up to install Python, like the PyNum and some other stuff, make sure that it was all installed on all the nodes, right? And there's some, and within, Hadoop and Yarn, there's easy ways to do that. But you do have to make sure it's on every node or in your jar. So, all right, so it's 12:22. We want to end at 12:30. Is that right? All right. So thank you, guys. I hope this was informational. Thank you.
Thanks, Mark. That was awesome. Great talk.